Look up at the night sky, and you'll see a sea of stars, steady, unchanging, eternal. But what if I told you some of those stars aren't as constant as they seem? Imagine a star shining brightly one moment, only to flicker out the next, as if something unseen is passing in front of it. This isn't science fiction. Astronomers have recorded dozens of cases where distant stars dim or vanish without warning, and no one knows exactly why. Could there be invisible structures, cosmic ghosts drifting through the darkness, blocking our view? Scientists call them spectral shadows, mysterious formations that defy detection yet leave behind clues in the flickering light of faraway suns. Think about the vastness of space for a moment. We're not just talking about planets or asteroids. These shadows would have to be colossal, stretching across entire solar systems, maybe even larger. And yet they're completely invisible to our telescopes. So what are they? Failed stars that never ignited, ancient remnants of shattered worlds, or something even stranger, something we haven't even begun to imagine? The universe is full of surprises, and this might be one of its greatest unsolved riddles. Tonight, we're going on a journey into the unknown, following the trail of these spectral shadows. We'll explore the baffling cases that have stumped astronomers, the wild theories that could explain them, and the cutting-edge technology that might finally reveal the truth. Because if these structures are real, they could rewrite what we know about the cosmos, about what's hiding in plain sight, just beyond our vision. So stay with me as we peel back the layers of this cosmic mystery, one flickering star at a time. One of the most baffling cases of vanishing starlight began in the constellation Cygnus, where astronomers watched a sun-like star called KIC 8462852 dim by a staggering 22%, far too much for a passing planet. Then, over days and weeks, its light flickered unpredictably, as if something vast and irregular were crossing in front of it. No known cosmic object behaves this way. Planets create smooth, rhythmic dips in starlight. Dust clouds scatter light evenly, but this was chaos, and it wasn't alone. Across the galaxy, telescopes have catalogued dozens of stars that dim erratically, some vanishing entirely for years before reappearing without explanation. So what's blocking their light? The leading theory, massive swarms of comets, quickly falls apart when you run the numbers. To dim a star that drastically, you'd need millions of comets packed impossibly close together, a scenario so unlikely it borders on fantasy. Others proposed rogue black holes or interstellar debris, but these would leave telltale gravitational or infrared signatures, none of which show up in the data. The truth is, conventional astronomy has no answer. That's why some researchers have turned to more radical ideas. What if these shadows aren't natural at all? Before you dismiss that as wild speculation, consider the scale. The structures eclipsing these stars would dwarf anything in our solar system. Imagine a megastructure so vast it could encircle a star, built by a civilization harnessing its energy. It sounds like science fiction, but astronomers take the hypothesis seriously enough to search for geometric patterns in the dimming evidence of artificial design. So far, none have been found, yet the mystery persists, a cosmic whodunit written in missing starlight. Whether natural or not, these shadows force us to confront how little we truly understand about the dark spaces between the stars. When astronomers first noticed stars vanishing without explanation, their initial reaction was skepticism. Could these anomalies simply be glitches in the data? Telescopes, after all, are intricate machines. Cosmic static, sensor malfunctions, or even space dust interfering with lenses might mimic the effect of a disappearing star. But as observations piled up across multiple observatories, that explanation crumbled. The dimming events were too consistent, too precise to be written off as technical hiccups. If the instruments weren't lying, then something truly bizarre was happening out there. Then came the hunt for natural culprits. the first suspect, rogue planets, worlds untethered from their stars drifting through interstellar space. But planets, even massive ones, only block a fraction of a star's light. These shadows were swallowing entire percentages. Next, astronomers considered dense molecular clouds, cosmic leftovers from star formation. Yet clouds don't move in such sharp, unpredictable patterns, nor do they vanish without leaving traces of gas or radiation. Even black holes, those invisible gravity wells, would betray their presence by warping the starlight around them, an effect conspicuously absent in these cases. The real turning point came when researchers realized these shadows didn't behave like any known celestial object. They weren't just blocking light, they were doing it asymmetrically, erratically, as if their shapes shifted over time. That's when the wilder theories took flight. Could these be fragments of shattered stars, supernova debris so dense it casts a perfect blackness? Or perhaps dark matter, the universe's most elusive substance, clumping in ways we've never detected? Each idea held tantalizing potential, but none could fully explain the sheer scale and strangeness of the phenomenon. This mounting frustration paved the way for the spectral shadows hypothesis. If none of the universe's usual players fit the bill, maybe the answer lay in something entirely new. Imagine structures woven from exotic matter, invisible to our telescopes yet dense enough to eclipse stars. Or remnants of a long-dead civilization's technology, lingering like cosmic driftwood. Far from science fiction, these possibilities forced astronomers to confront an exhilarating truth. The universe might still hold entire categories of objects we've never dreamed of. And that's the real magic of this mystery, not just the shadows themselves, but the door they've kicked open in our understanding of the cosmos. Dark matter has always been the universe's most frustrating puzzle, an invisible substance that outweighs all visible matter 5-1, yet refuses to show itself. We know it's there because its gravity tugs at galaxies, bending light like a cosmic funhouse mirror. But what if it's doing more than just lurking in the background? What if dark matter isn't just a diffuse haze but clumps together in ways so strange, so dense, it could cast shadows across the stars? Think of dark matter like an ocean current, usually smooth and undetectable, but under the right conditions, it might form whirlpools or eddies. Some theories suggest these clumps could grow massive enough to eclipse starlight, acting like cosmic curtains drawn across the sky. The catch: dark matter doesn't interact with light the way ordinary matter does. It wouldn't just block starlight, it would warp it, bending photons around its edges like water flowing around a rock. That could explain why these shadows leave no heat signature, no debris, just a star that flickers as if something unseen is passing by, the most compelling part. We've already seen hints of this. In 2018, astronomers studying a distant quasar noticed its light had been magnified and split into multiple images, a classic sign of gravitational lensing where mass bends spacetime to distort our view. But here's the twist: there was no visible galaxy or cluster causing the distortion. The culprit, likely a rogue clump of dark matter drifting silently between galaxies. If dark matter can do that, who's to say it couldn't form even larger, more complex structures, ones that just happen to line up perfectly between us and unsuspecting stars? Of course, not every scientist is convinced. Critics argue that dark matter, by its very nature, should spread too thinly to create such sharp, localized shadows. They point to supercomputer simulations showing dark matter as a fine, elusive web not dense enough to blot out stars, but simulations aren't perfect. What if we're missing a piece of the puzzle? Some researchers speculate that certain dark matter particles might interact weakly with each other, allowing them to clump in ways we haven't modeled yet. Others propose exotic forms of dark matter, like macros, theoretical particles as massive as asteroids that could, in theory, block light without emitting any of their own. The beauty of this mystery is how it forces us to rethink the boundaries of physics. if dark matter really is behind these spectral shadows, it's not just hiding in plain sight, it's sculpting the cosmos in ways we're only beginning to grasp. And that's the thrill of astronomy. Sometimes the most profound discoveries start with nothing more than a flicker in the dark. Picture the fabric of space-time not as a smooth, unbroken sheet, but as a bubbling sea of quantum foam, a chaotic, microscopic landscape where space itself constantly churns at the smallest scales. According to some of the most daring theories in physics, these fleeting irregularities could be the key to our cosmic shadows. Think of it like wrinkles in a vast cosmic blanket. Normally, these tiny ripples are too small to notice, but what if under the right conditions they could stretch, warp, or even knot into something large enough to cast a shadow across the stars? This isn't just speculation. Quantum foam is a prediction of quantum mechanics, where space-time isn't perfectly smooth but seethes with tiny, Planck-scale fluctuations. Most of the time, these vanish too quickly to affect anything, but some physicists argue that in rare cases, these fluctuations could amplify, creating temporary defects like tiny cracks or folds in reality itself. If one of these defects grew large enough, it might briefly distort the light from a distant star, making it flicker or vanish without leaving a trace. The real twist: these defects wouldn't behave like ordinary matter. They wouldn't reflect light, emit heat, or obey the usual rules of gravity. They'd be more like cosmic mirages, they're one moment, gone the next. That could explain why our telescopes see nothing in the way of these stars, even as their light dims unpredictably. It's as if space itself is momentarily twisting in just the wrong way, casting a shadow we can't directly see. Then there's the wild card: cosmic strings, these hypothetical, thread-like defects in space-time, left over from the Big Bang, could stretch across the universe like invisible fault lines. If one passed in front of a star, its immense gravitational pull could bend light around it, creating not just a dimming effect but bizarre optical distortions, multiple images of the same star, or sudden flares as light gets squeezed through the defect. While no definitive cosmic string has been found yet, their theoretical properties match some of the stranger patterns in these vanishing star events. Of course, not everyone's convinced. Critics point out that quantum foam and cosmic strings remain unproven, existing more in equations than in observational data. But that's the thrilling thing about astronomy. Sometimes the most outlandish ideas turn out to be true. After all, black holes were once considered mathematical curiosities too. Now we photograph them, so whether it's quantum foam, cosmic strings, or something even stranger, these shadows might be our first glimpse of a hidden layer of reality, one where space itself is far more dynamic and far more mysterious than we ever imagined. What if these shadows aren't just hiding in our universe? What if they're slipping in from somewhere else? Imagine a higher dimensional object, something beyond our familiar 3 dimensions, passing through our cosmic neighborhood like a ship cutting through fog. To us, it would appear as nothing more than a fleeting darkness, a distortion in starlight with no physical form. But in its own reality, it might be as solid and ordinary as a planet or a star. This isn't just wild speculation, it's a fringe idea with roots in some of the most cutting-edge physics theories out there. Take string theory, for example. It suggests our universe might be just one slice of a much larger multiverse, with other dimensions folded tightly around us, too small to detect. But what if those dimensions aren't always so hidden? Some physicists speculate that objects from these higher dimensions could occasionally brush against our own, leaving behind temporary imprints, like a hand pressing into a sheet of fabric. If one of these objects drifted between us and a star, it wouldn't just block light. It might bend it in ways we've never seen, creating a shadow that defies all conventional explanations. Even stranger is the idea of brains, short for membranes, enormous structures theorized to exist in higher dimensional space. Picture our entire universe as a flat sheet floating in a vast multidimensional ocean. Other brains might drift nearby, and if one grazed ours, the collision could unleash energy or distortions on a cosmic scale. But what if these interactions aren't always violent? A gentle nudge might send a fragment of another brain tumbling through our space, briefly eclipsing a star before vanishing without a trace. The beauty of these ideas is how they turn the problem on its head. Instead of searching for invisible objects within our universe, we're considering the possibility that the shadows aren't from here at all, and that opens up a dizzying array of questions. Could these higher dimensional visitors be predictable? Do they follow patterns we just haven't recognized yet, or are they as random as raindrops, impossible to forecast? Of course, not everyone's ready to rewrite the textbooks. Critics argue that without concrete evidence, these theories remain in the realm of mathematical fantasy. But history has shown us time and again that the universe loves to defy expectations. Black holes, dark energy, even the Big Bang, all were once dismissed as too outrageous to be real. So while interdimensional intruders might sound like science fiction, they're a reminder of how much we still don't know. And sometimes the most thrilling answers lie just beyond the edge of what we can see. Gravity bends light. That's something astronomers have known for over a century. When a massive object like a galaxy or black hole sits between us and a distant star, its gravitational pull warps space-time, acting like a cosmic magnifying glass. The star's light doesn't just dim, it stretches, splits, or even forms a glowing ring around the object. This phenomenon, called gravitational lensing, is one of the universe's most reliable tricks. But spectral shadows, they're not playing by the same rules. Take the famous Einstein cross, where a single quasar appears as four mirrored images around a foreground galaxy. That's gravitational lensing at work, predictable, symmetrical, and tied directly to the mass causing it. Now contrast that with the erratic dimming of stars like KIC 8462852. There's no symmetry, no telltale warping of light, just abrupt, jagged dips in brightness as if a jagged, invisible curtain were being drawn across the star. Gravitational lensing smooths and distorts, spectral shadows chop and obscure. Another key difference, heat. When gravity bends light, the intervening object, whether a galaxy or a black hole, leaves fingerprints. It might emit radiation, distort background starlight in specific ways, or reveal its presence through subtle temperature shifts. Spectral shadows leave nothing behind. No heat signature, no scattered light, no warped images, just cold, clean darkness. It's the difference between watching light bend through a prism and staring at a hole punched in the sky. But here's where it gets even stranger. Gravitational lensing follows strict rules. The amount of bending depends on the mass of the object and its distance from us. That's why astronomers can use it to weigh entire galaxies. Spectral shadows defy this logic. Their effects don't scale neatly with distance or predicted mass. Some stars dim for days, others for years, with no apparent pattern. It's as if the shadows aren't just passing through space, they're interacting with it in ways we don't yet understand. This isn't just a quirk of observation, it's a fundamental divergence. Gravitational lensing confirms our models of the universe, spectral shadows challenge them. One is a cosmic signpost pointing us toward hidden mass. The other is a riddle written in disappearing ink, and that's what makes this mystery so thrilling. It's not just about what's blocking the light, but why our usual tools for decoding the cosmos keep coming up short. In the year 1437, Korean royal astronomers meticulously recorded something unsettling in their celestial logs. A star in the constellation Scorpius, bright enough to be seen with the naked eye, simply vanished. No gradual dimming, no explosive finale. One night it shone steadily, the next it was gone. These weren't casual skywatchers, these were trained observers, backed by the precision of the Joseon dynasty's astronomical instruments, documenting the heavens for both science and omens. Their records were so detailed, so methodical, that modern astronomers still reference them today. And that's what makes this case so compelling. Could this have been one of the earliest documented encounters with a spectral shadow? Let's break down what they saw. The star, noted as guest star in their records, a term used for unexpected celestial visitors, wasn't behaving like a supernova. Those cataclysmic explosions leave behind glowing remnants or neutron stars, detectable even centuries later. Yet scans of that patch of sky reveal nothing, no debris, no fading echo of a stellar death. Just silence. The Korean accounts also mention no tail or vapor, descriptions they'd often use for comets. So if it wasn't a dying star or a wandering ice ball, what blotted out that pinpoint of light so completely? Here's where things get eerie. Modern astronomers revisiting the data have calculated that the star's disappearance was too abrupt for any known cosmic event. Supernova fade over months or years. Planets transit in predictable, hours-long dips, but this, gone in a night. The only natural explanation that comes close is a fast-moving, dense object, something like a rogue black hole. But even that falls short. A black hole's gravity would lens the star's light, warping it into rings or arcs, not snuffing it out cleanly. And there's another catch. Black holes that size would be exceedingly rare, making it statistically unlikely that one just happened to drift perfectly between Earth and that star at the exact moment astronomers were watching. That leaves us with two possibilities. Either the Korean astronomers witnessed a freakishly rare cosmic alignment, something so improbable it borders on miraculous, or they recorded something else entirely. Something that doesn't fit our current playbook of celestial phenomena. Could it have been a spectral shadow, a vast, unseen structure passing silently through the cosmos, casting its darkness like a ship's silhouette against a lighthouse beam? The timing fits. Unlike modern telescopes which monitor stars continuously, 1437's observers only saw snapshots night after night of clear skies, then sudden absence. If a shadow drifted by over weeks or months, they might have only caught the moment it fully eclipsed the star. Skeptics argue that historical records, no matter how precise, can't compete with modern data. Maybe the star was a variable one that dims naturally, or perhaps it was obscured by interstellar dust. But here's the counterpoint. Korean astronomers documented hundreds of variable stars and comets without confusion. They knew the difference between a fading light and a vanishing act, and dust, it scatters light, creating a hazy glow, not a clean disappearance. What if we're not just looking at an ancient mystery, but a recurring one? Fast forward to the 20th century, when astronomers at Harvard's observatory noticed plates of the same region showed a star present in 1945 and missing by 1950. No explosion, no gradual dimming, just another star blinking out of existence. Coincidence, maybe, but when you line up these accounts, 1437, 1950, the modern vanishing stars like KIC 8462852, a pattern emerges. Not of stellar death, but of something far stranger, celestial interruptions, brief, unexplained eclipses from objects we still can't see, the chilling takeaway. Spectral shadows might not be new. They might have been hiding in plain sight for centuries, scribbled in the margins of history by astronomers who had no framework to understand what they'd witnessed. And that raises a tantalizing question. If we comb through enough old records, could we find more of these ghostly visitations, tracing their path through the cosmos? The past might hold clues to a mystery we've only just begun to unravel. Modern telescopes have turned the hunt for spectral shadows into a high-stakes game of cosmic detective work. The Hubble Space Telescope, with its razor-sharp vision, has spent decades scanning the skies for anomalies, but it's the James Webb Space Telescope, with its infrared eyes, that might finally crack this mystery. Unlike Hubble, which sees the universe in visible light, Webb peers through cosmic dust and gas, revealing hidden structures that would otherwise stay invisible. Yet, even with these technological marvels, the challenge isn't just finding shadows, it's proving they're real. every flicker of starlight has to pass through a gauntlet of scrutiny. Is it a passing asteroid, a glitch in the telescope's sensors, maybe a cosmic ray hitting the detector just the wrong way? Scientists have to rule out dozens of mundane explanations before even considering something as exotic as a spectral shadow. Take the infamous alien megastructure star, KIC 8462852. Early observations suggested its bizarre dimming patterns might be artificial until follow-up studies revealed comets or dust could almost explain the data. Almost, that's the problem. These shadows thrive in the gaps, the almosts, the moments where conventional explanations fall just short. The real breakthrough might come from combining forces. Hubble's precision, Webb's infrared vision, and ground-based telescopes tracking star movements could create a multi-wavelength net, catching shadows no single instrument could confirm alone. Imagine Webb spotting a star dimming in infrared while Hubble sees nothing in visible light, a telltale sign of something that absorbs light but doesn't reflect or emit it. That's the kind of data that could turn speculation into science, but the clock is ticking. Some of these shadows seem to appear only once, vanishing before follow-up observations can lock them down. Others linger for years, then fade without explanation. It's a race against time and against the universe's knack for keeping its deepest secrets just out of reach. One thing's certain, if these shadows are real, they're not just hiding in the darkness. They're hiding in plain sight, daring us to see what we've been missing all along. What if I told you the key to cracking the spectral shadows mystery might not be in a high-tech lab, but on the laptop of someone like you? That's the power of citizen science, where everyday stargazers, armed with curiosity and a home computer, are helping astronomers scour the cosmos for these elusive anomalies. Projects like Zooniverses, Planet Hunters, and Backyard Worlds have turned millions of volunteers into cosmic detectives, sifting through mountains of telescope data that even supercomputers struggle to process. And the results, they're rewriting the playbook on how we explore the universe. Take the case of Tabetha Boyajian's star, the one with the infamous erratic dimming. It wasn't a team of PhDs who first spotted its bizarre behavior. It was volunteers on Planet Hunters flagging irregularities in Kepler Space Telescope data that algorithms had missed. These amateurs noticed something the professionals hadn't: dips in starlight that didn't fit any known pattern. Without them, the star might have been dismissed as a glitch. Instead, it became one of astronomy's most tantalizing puzzles. Here's the beauty of these projects: they don't require a telescope or a degree in astrophysics. Platforms like Zooniverse train you to spot anomalies, sudden brightness drops, asymmetric dimming, or stars that vanish entirely using real data from telescopes like TESS or Gaia. Some volunteers focus on identifying known objects like asteroids or exoplanets, while others hunt for the truly weird, the outliers that could be spectral shadows. And when enough eyes flag the same strange signal, professionals take notice. The impact goes beyond just cataloging oddities. In 2017, citizen scientists on Backyard Worlds discovered a previously unknown type of celestial object, a brown dwarf so cold it barely glows, lurking right in our cosmic backyard. These failed stars could be hiding in vast numbers, invisible to conventional surveys. If cold brown dwarfs can evade detection, what else might be out there? The same techniques used to find them could uncover those larger, stranger shadows blocking distant suns. Want to join the hunt? It's as simple as creating a free account on Zooniverse and diving into their astronomy projects. You'll start with tutorials teaching you to read light curves, graphs of a star's brightness over time, and how to tag suspicious dips or patterns. The interface feels almost like a game, with each click bringing you closer to a potential discovery. And if you're the first to spot something groundbreaking, you could earn co-authorship on a scientific paper, like the dozens of volunteers already credited in major astronomy journals. But here's the real magic: you're not just analyzing data, you're part of a global community. online forums buzz with volunteers comparing notes, debating whether a flicker is a planet transit or something stranger. Professional astronomers often jump into these discussions, offering insights or requesting deeper dives into intriguing finds. It's a rare collaboration where anyone, from a high school student to a retired engineer, can contribute to cutting-edge science. Of course, the work isn't always glamorous. For every potential breakthrough, there are thousands of false alarms, dust on telescope lenses, cosmic rays, or software artifacts. Yet persistence pays off. In 2021, a German schoolteacher sorting through Zooniverse data helped identify a neutron star spinning at an astonishing 700 times per second, one of the fastest ever recorded. If objects that extreme can hide in plain sight, what other surprises might patient observers uncover? This isn't just about outsourcing busy work. Humans still outperform machines when it comes to recognizing patterns that don't fit the mold. Our brains excel at spotting the "this doesn't belong" moments, the very skill needed to catch spectral shadows in the act. And with new telescopes like the Vera Rubin Observatory set to flood scientists with more data than ever, the need for sharp-eyed volunteers will only grow. So while billion-dollar instruments scan the skies, the next big discovery might come from your living room. All it takes is a willingness to look closely and the imagination to wonder what's lurking in the data's shadows. After all, the universe doesn't care who solves its mysteries. It just waits for someone to notice. Astronomy has entered a new era, one where artificial intelligence sifts through the cosmos like a digital detective, scanning billions of data points for clues humans might miss. Machine learning algorithms trained on vast archives of starlight measurements are now hunting for the faintest whispers of spectral shadows. These systems don't just analyze data, they learn from it, spotting patterns so subtle they'd slip past even the most meticulous human observer. Consider the numbers. The Kepler Space Telescope alone logged brightness readings from over 150,000 stars, each measured every 30 minutes for years. That's trillions of data points. No team of astronomers could process that manually, but AI can, and it's uncovering anomalies that defy explanation. Take the case of a star in the Milky Way's outer reaches. Its light curve, the graph tracking its brightness, showed erratic dips, but nothing that matched known planet transits or stellar flares. Traditional analysis dismissed it as noise. Then a neural network designed to flag unknown unknowns zeroed in on it. The pattern wasn't random. The dimming followed a faint, irregular rhythm, like something with structure was passing in front of the star. Not a solid object, but not a gas cloud either. Human researchers had overlooked it because it didn't fit existing categories. The AI had no such biases. It simply asked what doesn't belong. What makes machine learning so powerful in this hunt is its ability to spot one in a million events without preconceptions. Most algorithms are trained on normal stellar behavior, planetary transits, pulsations, flares, then set loose to find outliers. Some use unsupervised learning, clustering data into groups based on similarity. When a star's light curve lands in a cluster all by itself, that's a red flag. Others employ anomaly detection models which assign weirdness scores to each dataset. The higher the score, the more likely the star is hiding a secret, but AI isn't infallible. The same flexibility that lets it find novel patterns also makes it prone to false positives. Glitches, cosmic rays, or even telescope jitter can trick it into seeing shadows where none exist. That's why the best systems work in tandem with human intuition. For example, the Vera C. Rubin Observatory's upcoming 10-year sky survey will generate petabytes of data nightly. Its AI pipelines will flag potential oddities, but astronomers will vet each candidate, separating cosmic ghosts from technical gremlins. One groundbreaking approach involves adversarial networks, where two AIs duel to sharpen their skills. The first generates simulated light curves with artificial shadows, while the second tries to distinguish real data from fakes. over millions of iterations, both improve, one at crafting convincing decoys, the other at spotting them. The result, a system hyper-attuned to the slightest irregularities. Early tests have already identified stars with dimming patterns unlike anything in the training data, hinting that the universe might be weirder than our simulations. Yet the biggest challenge isn't just finding these shadows, it's interpreting them. When an AI flags a star as anomalous, scientists still face the puzzle of why. Is it an undiscovered celestial phenomenon, a flaw in the model, or something truly beyond our current physics? Here, AI becomes a collaborator, not just a tool. By generating hypotheses, could this pattern match a theoretical dark matter clump, a quantum spacetime defect? It sparks new lines of inquiry. The answers, when they come, might not just solve the mystery of spectral shadows, but reveal entirely new chapters in astrophysics. And that's the real promise of this partnership between human curiosity and machine precision. Together, we're not just searching the cosmos, we're learning how to see it anew, filtering out the noise to catch the faintest echoes of the unseen. Mathematical models are the backbone of modern astrophysics, the invisible scaffolding that lets us test wild ideas against the cold, hard rules of the universe. When it comes to spectral shadows, physicists don't just throw up their hands and guess. They build intricate simulations, equations that map how hypothetical objects would warp starlight, then compare those predictions to the flickers we actually see. It's like reconstructing a crime scene from a single blurry photograph, working backward to figure out what could have cast that shadow. Start with the simplest case, a solid, spherical object passing in front of a star. The math here is straightforward geometry meets basic optics. As the object transits, the star's brightness drops smoothly, forming a U-shaped curve in the light graph. But spectral shadows don't play by these rules. Their dimming patterns are jagged, asymmetrical, sometimes even staircase-like. That's when physicists reach for more complex tools like fractal geometry or n-body simulations to model objects with irregular shapes or dynamic structures. Imagine simulating a swarm of debris, each fragment moving independently, casting overlapping shadows that morph over time. The equations quickly spiral into chaos, requiring supercomputers to crunch the numbers. One breakthrough came from adapting fluid dynamics equations to these cosmic puzzles. Turbulence, the same math used to predict weather patterns or ocean currents, can describe how clumps of dark matter or exotic particles might ripple and clump, creating fleeting patches of density thick enough to block light. These models produce shadows that appear and vanish erratically, matching some of the strangest observations. But there's a catch. Turbulence usually requires a medium like air or water. Apply it to the near vacuum of space and you're left with a haunting question: what's flowing out there? Then there's gravitational microlensing, a gold standard for detecting invisible mass. The equations here are elegant. Einstein's general relativity predicts exactly how a foreground object's gravity bends light, amplifying a star's brightness in a predictable curve. But spectral shadows flip this script. Instead of brightening, the star dims and the equations break. Some theorists tweak the models by adding negative mass or repulsive gravity, concepts that border on science fiction. Others explore modified gravity theories where the rules change at cosmic scales. Every tweak generates new predictions. If the shadow is caused by X, the star should flicker in Y way. Then astronomers cross-check those predictions against real data, like detectives comparing a suspect's alibi to security footage. The most tantalizing models come from quantum physics. Simulating quantum foam, the frothy, fluctuating fabric of spacetime at microscopic scales, requires mind-bending math like Wheeler-DeWitt equations or loop quantum gravity. These aren't just number-crunching exercises, they're explorations of reality's underlying structure. When researchers scale these quantum effects up to astronomical sizes, the models produce shadows that flicker in and out of existence, matching reports of stars that vanish for years before reappearing unchanged. It's as if space itself has tiny cracks, and when one aligns just right, it casts a shadow across the cosmos. Yet for all their sophistication, these models share one humbling limitation: they're only as good as our imagination. Every simulation starts with assumptions about the shadow's composition, its density, how it interacts with light. If we're missing a fundamental piece of physics, our models might be like medieval astronomers trying to plot planetary orbits without calculus. That's why each new observation is gold dust. When a star dims in ways no equation predicts, it's not a failure. It's a clue, a signpost pointing toward physics we've yet to invent. The beauty of this mathematical hunt: even the wildest theories get a fair shot. String theory, higher dimensions, even alien megastructures, all can be translated into equations, their shadows plotted on a graph. The universe doesn't care if an idea sounds outlandish. It only cares if the numbers add up, and that's how we'll solve this mystery: one equation, one observation, one unimaginable shadow at a time. Picture the universe not as a vast emptiness, but as an intricate tapestry, one that might contain tiny, invisible flaws woven into its very fabric. These hypothetical imperfections, known as cosmic strings, are thought to be remnants of the Big Bang, infinitely thin threads of energy, thinner than a proton but denser than a mountain range. If they exist, they'd stretch across the cosmos like cracks in frozen ice, carrying the imprint of the universe's earliest moments. And here's where it gets fascinating: their immense density could warp space-time so severely that passing starlight would bend around them, creating fleeting shadows we might mistake for spectral phenomena. Unlike black holes or planets, cosmic strings wouldn't block light the conventional way. Instead, their gravitational pull would act like a funhouse mirror, distorting the path of photons in bizarre ways. Imagine a star's light splitting into multiple images around an unseen filament, or flickering as the string's immense tension sends ripples through space-time itself. Some models even suggest these strings could oscillate, vibrating like guitar strings plucked by the cosmos, each oscillation casting shifting, asymmetrical shadows that defy explanation. The wildest part: cosmic strings might not even obey the usual rules of gravity. Unlike planets or stars, their gravitational influence wouldn't weaken with distance in the typical way. A string a light year away could tug on starlight just as fiercely as one right next to it, creating lensing effects that appear and vanish without warning. That could explain why some stars seem to dim erratically with no visible culprit. It's as if the shadow isn't attached to anything tangible, just a kink in the fabric of reality, briefly interrupting the light. But why haven't we detected them yet? The challenge lies in their scale. A cosmic string could slice cleanly through our solar system without us noticing, unless it happened to line up perfectly with a distant star. Even then, its shadow would be razor thin, a momentary slit of darkness crossing a star's face. Telescopes would need near-perfect alignment and timing to spot it. Yet there's hope. Some physicists argue that if strings exist, they might reveal themselves through gravitational waves. The snap of a vibrating string could send ripples through space-time detectable by observatories like LIGO, offering indirect proof of these cosmic threads. Skeptics point out that cosmic strings remain purely theoretical, with no direct evidence to date, but their potential to explain spectral shadows is too compelling to ignore. After all, the universe has a habit of turning mathematical curiosities into reality. Black holes were once dismissed as calculator quirks before we photographed them. Whether cosmic strings are the answer or just another piece of the puzzle, they remind us that the darkest corners of space might be hiding flaws in the very canvas of existence. And that's a mystery worth unraveling. Black holes don't just swallow light, they play with it. When a star ventures too close, the black hole's gravity shreds it into a swirling stream of superheated gas, a process called a tidal disruption event. For months, even years afterward, that material spirals inward like water down a drain, glowing fiercely as it vanishes. But here's the twist: some of that light doesn't escape straight to our telescopes. It ricochets off warped space-time near the black hole's edge, creating faint, delayed copies of the original flare, what astronomers call light echoes. And these echoes might hold the key to a cosmic case of mistaken identity. Imagine a black hole's echo as standing in a hall of mirrors. You see your reflection not just once, but over and over, each version slightly distorted and arriving a fraction of a second later. Now scale that up to galactic proportions. Light bouncing off the twisted space around a black hole could reach us years after the initial burst, stretched and dimmed by its journey. To an unsuspecting observer, that delayed light might look like a shadow, a patch of darkness moving across a star as if something solid were blocking it. But there's no physical object there, just the ghostly afterimage of a black hole's meal echoing across the cosmos. This isn't just speculation. In 2022, researchers studying a tidal disruption event in a galaxy 650 million light-years away spotted something bizarre. After the initial flare faded, the star's location flickered back to life months later, not with fresh energy, but with an eerie replay of the original outburst. The team calculated that this echo had traveled an extra 200 billion miles, detouring around the black hole's gravitational whirlpool before finally escaping. If such an echo happened to cross paths with another star's light on its way to Earth, it could create the illusion of a spectral shadow, a temporary dimming with no apparent cause. The debate hinges on timing. True spectral shadows like those from hypothetical dark matter clumps or megastructures would block starlight in predictable, repeatable patterns. But echoes, they'd be one-offs tied to specific black hole activity in the distant past. Here's where it gets tricky. The echoes could be spread over centuries. A single tidal disruption event might produce dozens of light paths, each taking a different route through the black hole's warped surroundings. Some might arrive decades apart, creating sporadic, unpredictable dimming that defies conventional explanation. Critics argue that echoes can't explain all vanishing star cases. The dimming would have a distinct spectral fingerprint, specific wavelengths of light altered by their turbulent journey, whereas some observed shadows show no such distortion. Others counter that our instruments might not be sensitive enough to detect those subtle changes yet. The James Webb Space Telescope's infrared eyes could settle the debate, probing these events for the telltale signs of stretched and scattered light. The most tantalizing possibility: some shadows might be both echoes layered atop real obstructions. Picture a rogue planet or dust cloud drifting into view just as a black hole's ancient echo passes behind it. The combined effect could create a light curve so bizarre it defies all existing models. That's the maddening beauty of astronomy. The universe loves to mix its mysteries. Whether echoes, shadows, or something else entirely, each flicker of starlight is a breadcrumb trail leading us deeper into the dark. What if the key to these cosmic shadows isn't hidden in distant galaxies, but in the very fabric of reality itself? Meet Action's hypothetical particles so lightweight and elusive, they've been called ghosts of the quantum world. Theorized to solve a decades-old puzzle in particle physics, these strange entities could be floating through space in vast, invisible clouds. Normally, actions would zip right through matter like it wasn't even there, barely leaving a trace. But under extreme conditions, say near a neutron star's crushing magnetic field, they might clump together, forming structures dense enough to bend or even block light. Picture a fog so fine you could walk through it without feeling a thing, yet when viewed against a bright light, it casts a faint, shifting shadow. Then there's WIMP, weakly interacting massive particles, the heavyweight contenders in the dark matter hunt. These hypothetical particles are thought to outweigh protons by 100 times or more, yet they almost never bump into ordinary matter. That's what makes them weakly interacting. But here's the twist: if WIMP exist, they might occasionally collide and annihilate each other, releasing bursts of energy. In regions where dark matter is densely packed, like the cores of galaxies, those interactions could create temporary pockets of distorted space regions where light gets briefly trapped or scattered. To an observer on Earth, it might look like a star's light dimmed for no reason, when in truth it passed through a swirling vortex of invisible particles. The wildcard cue balls, these theoretical blobs of condensed matter predicted by some supersymmetry models, could grow to asteroid-sized masses while remaining nearly transparent. Unlike solitary particles, cue balls behave more like liquid droplets, absorbing energy without radiating it back. If one drifted in front of a star, it might not just block light, it could slowly siphon the star's energy, causing a gradual, unnatural dimming that lasts for centuries. Critics argue that these ideas stretch credibility. Action clouds would require conditions so precise they'd be rarer than diamonds in a comet's tail. WIMP interactions, if they happen at all, would likely be too feeble to noticeably dim starlight, and cue balls, no one's ever detected even a whisper of their existence. But here's where the skeptics might be missing the bigger picture. The universe doesn't care what we deem likely. It's already shown us phenomena like gamma-ray bursts or colliding neutron stars that once seemed impossible. If exotic matter can form, even under vanishingly rare circumstances, then somewhere in the cosmos, it's probably sculpting shadows we've yet to understand. Perhaps the most tantalizing clue lies in an accidental discovery from 2019. Astronomers mapping the cosmic microwave background, the afterglow of the Big Bang, found strange, thread-like fluctuations in the data. Some speculated these could be scars from early universe phase transitions, where exotic matter briefly dominated space. If remnants of that era survived, floating between galaxies like cosmic cobwebs, they might explain why certain stars flicker as if something unseen is tugging at their light. The bottom line: we're searching for needles in a universe-sized haystack, needles that might not even be made of metal. But every unexplained dimming, every anomalous flicker, is a breadcrumb leading us closer to answers that could rewrite the rules of physics. Whether it's actions, WIMP, or something even stranger, one thing's certain: the shadows haunting our telescopes aren't just gaps in our data, they're windows into a hidden layer of reality. The eerie silence of the cosmos has haunted astronomers for decades. Where are all the aliens? This question lies at the heart of the Fermi paradox, the unsettling disconnect between the universe's vast age and the absence of detectable extraterrestrial civilizations. But what if we've been looking for the wrong signs? Instead of radio signals or laser beams, advanced societies might leave subtler traces, cosmic engineering on scales so immense they'd be mistaken for natural phenomena. That's where spectral shadows enter the conversation. Consider the staggering energy needs of a civilization millions of years ahead of us. They might harness entire stars, building vast megastructures like Dyson spheres, hypothetical shells that encapsulate a star to capture its energy. From our vantage point, such an object wouldn't glow like a normal star. It would emit waste heat in the infrared, and if incomplete or partially constructed, it could block starlight in erratic, asymmetrical ways. Sound familiar? The unpredictable dimming of stars like KIC 8462852 matches what we'd expect from a partially built Dyson swarm, a constellation of energy collecting satellites encircling a star. But why wouldn't we detect their infrared signatures? Advanced civilizations might have technologies far beyond our understanding, perhaps methods to recycle waste heat or channel it into other dimensions. Or maybe these structures are so old they've cooled beyond our detection limits, their builders long gone, leaving behind only skeletal remnants drifting through the galaxy. This wouldn't just solve the Fermi paradox, it would reframe it. The universe might not be empty, it could be littered with the archaeological ruins of civilizations that rose and fell before Earth even formed. Skeptics counter that invoking aliens is a last resort, a violation of Occam's razor. Yet history shows us that cosmic mysteries often demand radical solutions. Pulsars, discovered in 1967, were initially dubbed LGM signals, little green men, because their precise, repeating beats defied natural explanation. Only later did we understand them as spinning neutron stars. The lesson: sometimes the truth is stranger than fiction. Another possibility: what if these shadows aren't intentional constructions at all, but byproducts of cosmic engineering? Imagine a civilization mining a star's energy with stellar-scale machinery, accidentally ejecting vast clouds of debris or warping local space-time in ways that intermittently occlude their star. Or consider Shkadov thrusters, theoretical megastructures that use a star's own radiation pressure to steer it across the galaxy. The gravitational ripples and debris fields from such projects could create shadows visible thousands of light-years away. The chilling implication: if spectral shadows are evidence of intelligence, they might suggest a universe where advanced civilizations don't broadcast their presence, they obscure it. Whether out of caution, indifference, or motives beyond our comprehension, they'd leave behind only cryptic fingerprints, cosmic graffiti etched in missing starlight. That would make the Fermi paradox not a puzzle to solve, but a warning, a sign that the universe's greatest civilizations perfected the art of invisibility long ago. Yet there's hope in the silence. If these shadows are artificial, they're not just hiding places, they're invitations. Each unexplained dimming, each flicker without a known cause, is a potential handshake from the depths of time. And that changes the game entirely. The search for spectral shadows isn't just about solving an astronomical riddle. It's about learning whether we're alone, or whether something out there has been quietly watching all along. To uncover the secrets of spectral shadows, scientists are turning to the most powerful supercomputers on Earth, machines capable of simulating the universe itself. These towering stacks of processors hum with virtual galaxies, dark matter halos, and cosmic filaments, reconstructing the scaffolding of reality based on the laws of physics. The goal: to predict where invisible structures might hide by reverse engineering the cosmos. Start with dark matter, the invisible glue holding galaxies together. While we can't see it directly, its gravitational pull sculpts the distribution of visible matter like fingerprints on glass. Supercomputers like NASA, Pleiades, or the NSF's Frontier take real-world maps of galaxy clusters, then apply quantum mechanics and relativity equations to simulate how dark matter should be arranged. The resulting models reveal a cosmic web, vast threads of dark matter connecting galaxy clusters with dense knots where shadows might lurk. One simulation from the University of Zurich even predicted dark matter hurricanes, streams of invisible particles moving at 500 kilometers per second, which could briefly eclipse stars if they passed in front of them. But how do you test these predictions? Enter synthetic skies. Researchers program supercomputers to generate mock telescope observations, inserting hypothetical structures, cosmic strings, action clouds, rogue black holes into simulated star fields. Then they compare these artificial datasets to real observations of vanishing stars. It's like creating a digital twin of the universe, tweaking variables until the simulations match the anomalies we see. In 2023, a team at the Harvard-Smithsonian Center for Astrophysics ran this experiment with a startling result. Their models suggested that if just 1% of dark matter clumped into asteroid-sized macro particles, it would produce exactly the erratic dimming patterns plaguing astronomers. The real breakthrough came when simulations incorporated time. Most models treat the cosmos as a static snapshot, but reality is fluid. Stars move, dark matter drifts. A shadow blocking a star today might be light years away tomorrow. Dynamic simulations now track these shifts over millennia, revealing how transient cosmic alignments could create one-off vanishing acts. One simulation showed a star dimming for 50 years as an invisible dark matter filament passed by, only to brighten again as the filament drifted out of view. Uncannily, this matches historical records like the Korean guest star disappearance in 1437. Yet simulations have limits. They're only as good as the physics we input, and spectral shadows defy conventional rules. Some teams are now integrating machine learning, training AI to spot gaps in the model's places where simulated universes don't match our own. These discrepancy detectors flag phenomena the original programmers never anticipated, hinting at entirely new classes of objects. It's a cosmic feedback loop. Simulations guide observations, observations refine simulations, and somewhere in that dance, the truth about these shadows may finally emerge. The most tantalizing simulations explore alternative physics. What if dark matter interacts with itself, forming invisible galaxies? What if quantum fluctuations scale up to planetary sizes? One radical model from the Perimeter Institute even simulated universes with extra spatial dimensions, producing shadow-like distortions when higher dimensional objects intersected our three-dimensional plane. The math checks out, but without observational proof, these remain digital phantoms. What makes this computational hunt so thrilling is its scope. Every unexplained dimming event is a clue, a coordinate in a vast cosmic treasure map. And as supercomputers grow more powerful, they're not just solving mysteries, they're revealing how much we've yet to discover. The shadows flickering in our telescopes might be more than oddities. They could be the universe's way of whispering, "Look closer. There's so much more here than you can see." The flicker of a star might seem insignificant, a barely noticeable dip in brightness lost in the noise of the cosmos. But to astronomers, that tiny change is a scream in the silence, a clue etched in photons. That's where photometry comes in, the meticulous science of measuring starlight with precision so razor-sharp. It can detect a planet the size of Earth passing in front of a sun 1,000 light-years away. And when it comes to spectral shadows, photometry isn't just a tool, it's the flashlight we're shining into the dark, revealing gaps where something unseen is stealing the light. Picture a star's light curve, a graph tracing its brightness over time. Under normal circumstances, it's a near flat line, with gentle ripples caused by the star's own pulsations or the occasional passing asteroid. But when a spectral shadow drifts into view, the curve transforms. The dip isn't smooth like a planet's transit. It's jagged, asymmetrical, sometimes even stair-stepped, as if the shadow has a texture, a structure. That's the first red flag. Photometry doesn't just tell us a star dimmed, it tells us how, and that how is the fingerprint of the unknown. Take the Kepler Space Telescope's data on KIC 8462852. Most exoplanet hunts focus on U-shaped dips, clean, symmetrical shadows cast by spherical worlds. But this star's light curve looked like it had been chewed by cosmic termites. The dips varied wildly in depth and duration, some lasting days, others weeks, with no repeating pattern. Photometry ruled out planets, it ruled out comets. Even a rogue black hole would have left a gravitational lensing signature that wasn't there. What remained was a shadow with no obvious source, a void that photometry could measure but not explain. The secret to photometry's power lies in its precision. Modern instruments like the James Webb Space Telescope can detect brightness changes as small as 1 part in 100,000, equivalent to spotting a single candle flickering in a city of neon. That sensitivity lets astronomers dissect a shadow's structure. For example, if the dimming is sharper on one side than the other, the object might be elongated like a cosmic rod. If the light curve shows multiple tiny dips within a larger one, there could be substructure. Think of a swarm of debris with gaps between fragments. Photometry turns shadows into puzzles we can hold in our hands, even if we can't yet see the pieces. But raw data isn't enough. To separate true shadows from false alarms, sensor glitches, cosmic rays, even interstellar dust scientists use algorithms to filter out noise. One technique called difference imaging compares consecutive snaps of the same star, pixel by pixel. Real shadows persist across frames, noise flickers randomly. Another method, aperture photometry, measures light within a virtual ring around the star, catching subtle changes missed by broader surveys. It's like tuning a radio dial until static gives way to a signal. And sometimes that signal is a star winking out as something vast and invisible glides silently by. The most tantalizing photometric clues come from stars that don't just dim, they vanish entirely. In 2018, the VASCO project scanned decades of sky surveys and found at least 100 stars present in old photographic plates but missing in modern images. No explosions, no fading, just gone. Photometry's role here is forensic. By analyzing the last traces of light before disappearance, researchers can rule out catastrophic events like supernova, which leave lingering radiation. These stars didn't die, they were eclipsed, their light switched off like a bulb in a room we can't enter. Critics argue that photometry alone can't solve the mystery. It's a flashlight, not an X-ray, revealing shadows but not their substance. That's why it's often paired with spectroscopy, splitting starlight into wavelengths to hunt for chemical clues. Yet when spectroscopy finds no gas, no dust, no heat signature where a shadow lurks, photometry's cold, numerical truth becomes even more compelling. The light was blocked, something did this, and until we can peer behind the curtain, these precise, unblinking measurements are our best map to the unseen. In the end, photometry is more than a technical tool. It's a language, one that translates the silent, black gaps between stars into questions we can finally begin to ask. Every anomalous dip, every unexplained flicker is a word in that language, spelling out a story we're only starting to read. And with each new generation of telescopes, our vocabulary grows, bringing us closer to understanding what waits in the dark. Most cosmic mysteries reveal themselves in snapshots, a single, frozen moment captured by a telescope. But spectral shadows, they're shapeshifters, flickering in and out of view like whispers in a crowded room. That's where time-domain astronomy comes in. Instead of studying the sky as a static picture, it treats the universe like a movie, tracking how starlight changes over days, months, even decades. This isn't just about spotting shadows, it's about catching them in the act, distinguishing them from the countless other cosmic events that mimic their tricks. Think of it like listening to a symphony. A single note tells you very little, but play that note over time and patterns emerge, a melody, a rhythm, maybe even a mistake. Time-domain astronomy does the same with starlight. Take the case of a star that dims suddenly. Is it a spectral shadow, a dying star, or just a glitch in the data? By monitoring that star night after night, astronomers can rule out imposters. Supernova brighten before they fade. Planets cause predictable, repeating dips. But spectral shadows, they dance to their own erratic beat. The real power of this approach lies in its patience. Some shadows reveal themselves only after years of observation. A star might flicker once and never again, like a cosmic one-hit wonder. Others dim gradually over centuries, their slow fade lost in the noise unless you're watching closely enough. Projects like the Zwicky Transient Facility and the upcoming Vera Rubin Observatory are built for this very purpose, scanning vast swaths of sky night after night, compiling light curves for billions of stars, searching for the outliers that don't fit the script. But time-domain astronomy isn't just about collecting data, it's about context. A single dimming event might be intriguing, but a pattern of similar events across different stars. That's a clue. In 2020, researchers sifting through a decade of Kepler Space Telescope data noticed something peculiar. A handful of stars scattered across the galaxy had all dimmed in the same unusual way, sharp, irregular dips with no apparent cause. Isolating those events from the noise required comparing timelines, aligning observations, and ruling out local explanations. The result, a growing catalogue of anomalies that point to something stranger than instrument error or known astrophysics. Here's where the technique gets truly revolutionary. By stitching together historical records with modern observations, astronomers can trace potential shadows across centuries. Remember that Korean guest star from 1437? Time domain astronomy lets us treat it not as an isolated incident, but as one data point in a much longer timeline. When combined with later vanishings like the star that disappeared from Harvard's plates in the 1950s, patterns start to emerge. Maybe these aren't random events at all, but the signature of something cyclical, something vast moving through the galaxy on a scale we're only beginning to grasp. The challenge, of course, is scale. The universe is ancient, and humanity's detailed observations span barely a blip in cosmic time. That's why projects like the Legacy Survey of Space and Time will monitor the sky for a full decade, creating a movie of the universe with enough frames to catch even the most elusive shadows. Because if there's one thing time domain astronomy teaches us, it's that the cosmos doesn't keep hours. The truth might be hiding in the gaps between our observations, waiting for us to look long enough and smart enough to see it. Brown dwarfs linger in the cosmic shadows, too massive to be planets, yet too small to ignite as true stars. These failed stars smolder at temperatures barely warm enough to toast bread, emitting only a faint infrared glow. In theory, one drifting between us and a distant sun could dim its light, casting the kind of shadow astronomers have recorded. But here's the catch: brown dwarfs aren't invisible. Even the coldest among them, known as white dwarfs, radiate enough heat for infrared telescopes like the James Webb to spot. Yet in every documented case of spectral shadows, follow-up observations find no trace of thermal signatures. It's as if whatever's blocking the light isn't just cold, it's utterly undetectable at any wavelength. Then there's rogue planets, worlds untethered from their parent stars, wandering the interstellar void. Some, like the free-floating planet CFBD Sir 2149, are massive enough to rival small brown dwarfs. If one passed in front of a star, it could certainly cause a temporary dimming. But the numbers don't add up. A planet large enough to eclipse a star by 20%, as seen in cases like KIC 8462852, would dwarf Jupiter. Rogue planets that size are astronomically rare, and they'd leave gravitational fingerprints, subtle tugs on background stars or surrounding dust. Yet spectral shadows show none of these hallmarks. The real nail in the coffin: predictability. Planets and brown dwarfs obey the clockwork mechanics of orbital motion. Their transits are rhythmic, like a pendulum swing. If one dims a star today, it'll do so again in a calculable time frame. Spectral shadows laugh at this regularity. Their dimming is erratic, sometimes vanishing for decades before flickering back into view. A rogue planet can't decide to take a century-long break from eclipsing its star. But something else, something stranger, just might. There's another wrinkle: light distortion. When a planet or brown dwarf passes in front of a star, its atmosphere, if it has one, can subtly bend the starlight, creating telltale color shifts or refraction patterns. Spectrographs are exquisitely tuned to catch these effects. Yet spectral shadows show none of the atmospheric fingerprints you'd expect from a tangible object. It's as if the light isn't being bent or filtered, just cleanly snipped away. This isn't to say brown dwarfs and rogue planets aren't out there. They're fascinating in their own right, celestial nomads hinting at untold stories of chaotic star formation and violent planetary ejections. But when it comes to the spectral shadow mystery, they're more like red herrings than smoking guns. The shadows we're chasing don't just hide in the dark. They defy the very rules that govern everything else we've ever found in the cosmos. And that's what makes them so thrilling, not just for what they are, but for what they force us to question about the universe we thought we knew. The cosmic microwave background, the afterglow of the Big Bang, is like a fossilized fingerprint of the infant universe. This faint glow, visible in every direction, carries subtle temperature variations, imprints of density fluctuations from when the cosmos was just 380,000 years old. Normally, these patterns help us map the distribution of matter in the early universe, but buried in that static might be something stranger. The faint echoes of invisible structures vast enough to cast shadows across stars billions of years later. Take the cold spot, an anomaly in the CMB where temperatures dip more than expected. Stretching over 1 billion light-years, this region is too large and too cold to easily explain with standard cosmology. Some theorists propose it's the imprint of a cosmic texture, a defect in space-time left over from the universe's violent birth, like a wrinkle frozen in an expanding sheet. If such textures exist, they wouldn't just leave cold spots. They could persist as invisible knots in the fabric of reality, drifting through space and occasionally eclipsing stars in ways that mimic spectral shadows. Then there's gravitational lensing of the CMB itself. As the microwave background travels across the universe, massive objects bend its path, warping the temperature patterns we observe. Most of this lensing comes from known galaxy clusters, but some distortions don't match any visible mass, ghostly imprints that suggest hidden structures bending light from behind the cosmic curtain. These dark lenses align eerily with regions where astronomers report anomalous star dimming. Could the same invisible behemoths warping the CMB also be casting shadows in modern starlight? The most tantalizing clue comes from polarized light in the CMB. Certain polarization patterns, called B modes, can be caused by primordial gravitational waves, ripples from the universe's explosive first moments. But some B modes don't fit that model. Instead, they resemble what you'd expect if vast, sheet-like structures, cosmic domain walls, were vibrating through space. These hypothetical walls, relics of early universe symmetry breaking, would be nearly transparent yet dense enough to distort light. From our vantage point, they might appear as plane-shaped shadows drifting across stars, vanishing as quickly as they came. Critics argue that connecting CMB anomalies to modern star dimming is speculative at best. The universe has expanded by a factor of 1,000 since the CMB was emitted. Structures that left imprints then should be vastly diluted now. Yet alternative models suggest some defects could have survived, or even grown by feeding on dark energy. It's a radical idea that the same invisible scaffolding shaping the infant cosmos might still lurk in today's universe, occasionally stepping into the light, or rather, stepping between us and the light. The key to testing this lies in cross-referencing. Teams are now overlaying CMB anomaly maps with catalogs of vanishing stars, searching for spatial correlations. Early results hint that certain CMB cold spots align with lines of sight where multiple stars have shown unexplained dimming. It's not conclusive, not yet. But if the pattern holds, we might be looking at the same cosmic structures through two different lenses, their ancient imprint on the CMB and their modern shadow play on distant suns. What makes this possibility so profound is the timescale. If these shadows truly stem from primordial defects, they're not just objects in space, they're events in time, threads woven through the entire history of the cosmos. A star dimming tonight might be feeling the echo of a tremor from the universe's first second, and that changes everything. Suddenly, spectral shadows aren't just a puzzle to solve. They're a bridge, a way to peer past 13.8 billion years and touch the universe at its birth. The next generation of space telescopes won't just observe the cosmos, they'll hunt ghosts. Projects like the Nancy Grace Roman Space Telescope, set to launch in the late 2020s, are being fine-tuned to catch spectral shadows in the act. Unlike Hubble or Webb, which focus on deep field imaging, Roman will excel at time-domain surveys, scanning vast swaths of sky repeatedly to track how stars change over weeks, months, and years. Its wide-field instrument can monitor millions of stars simultaneously, creating a motion picture of the cosmos where even the subtlest flicker won't escape notice. With precision 10 times sharper than Kepler's, Roman could spot shadows too faint or fleeting for current telescopes, mapping their patterns across the Milky Way like a celestial census taker. Then there's LUVOIR, the Large Ultraviolet Optical Infrared Surveyor, a proposed flagship mission that could revolutionize our search. Imagine a telescope with a mirror over 15 meters wide, dwarfing Webb's 6.5 meters. That light-gathering power would let LUVOIR detect shadows blocking as little as 0.01% of a star's light, revealing structures too tenuous for today's instruments. Its ultraviolet capabilities add another weapon, the ability to spot the faint ionization trails that certain exotic objects like cosmic strings or dense dark matter clumps might leave behind. LUVOIR wouldn't just find shadows, it could dissect their composition by analyzing how different wavelengths of light are absorbed or bent. Ground-based projects are joining the chase too. The Vera Rubin Observatory's legacy survey of space and time will scan the southern sky every 3 nights for a decade, creating the most comprehensive time-lapse of the universe ever made. With a 3.2 billion pixel camera, it'll catch transient events older telescopes would miss, like a star vanishing for a single night, then reappearing untouched. Rubin's real power lies in synergy. Its alerts could trigger rapid follow-ups by Roman or Webb, creating a multi-observatory net to trap these elusive phenomena. The game-changer, polarimetry. Upcoming missions like the Imaging X-ray Polarimetry Explorer and the European Space Agency's Ariel will study how light's orientation changes when passing through potential shadow-causing objects. A cosmic string, for instance, would twist polarized light in a unique spiral pattern, while a dense dark matter knot might scatter it asymmetrically. These fingerprints could distinguish natural phenomena from something truly unprecedented. But perhaps the most daring proposal is Farside, a lunar radio telescope designed to peer into the universe's dark ages before the first stars formed. By detecting low-frequency radio waves bent by ancient structures, it might reveal whether spectral shadows are a modern anomaly or if they've haunted the cosmos since the beginning. These missions share one thrilling trait. They're not just built to confirm existing theories, but to stumble upon the unimaginable. Every time humanity has built a telescope with new capabilities, it's discovered something that rewrote the textbooks. If spectral shadows are out there, the next decade of astronomy won't just find them, it'll force us to ask what else we've been missing in the dark. The universe we see may be a carefully edited version of reality, a cosmic stage where most of the actors remain hidden in the wings. If spectral shadows are real, they force us to confront a humbling possibility. That light itself is an unreliable narrator, telling a story full of omissions and redactions. Consider how much of our cosmic knowledge comes from photons, the light of stars, galaxies, and the microwave background. But what if entire categories of objects don't interact with light at all? What if dark matter isn't the exception, but part of a vast, invisible ecology we've barely begun to map? This isn't just about missing pieces, it's about the nature of perception. Human eyes evolved to see a narrow band of electromagnetic radiation, what we call visible light, because those wavelengths dominated our planet's environment. But imagine a species that evolved in a dark matter-rich world. Their telescopes might ignore stars entirely, tuned instead to gravitational ripples or quantum fluctuations. To them, our visible universe could seem as ghostly and insubstantial as spectral shadows appear to us. The lesson: reality isn't an absolute. It's a negotiation between observer and environment, and we may be hopelessly out of sync with the cosmos's full spectrum. The implications ripple outward. Modern cosmology rests on the assumption that what we see is representative, that galaxies, quasars, and supernova paint an accurate picture of universal structure. But if substantial chunks of mass exist in forms that don't emit, reflect, or absorb light, our cosmic censuses could be off by orders of magnitude. The Milky Way might harbor invisible siblings, whole galaxies of shadow matter drifting unseen. The missing mass problem wouldn't just apply to galaxy clusters. It could rewrite the universe's entire inventory. More unsettling is the anthropic dimension. The fine-tuning argument, the idea that physical constants seem improbably perfect for life, assumes we're seeing all the variables. But if spectral shadows hint at hidden layers of physics, our fine-tuned universe might be an illusion, like a two-dimensional being marveling at how perfectly circles fit into their flat world, unaware of the third dimension where spheres exist effortlessly. Life didn't emerge in a universe fine-tuned for it. We're survivors in a cosmic labyrinth where most paths lead to oblivion, and our instruments barely scratch the surface of what's out there. Perhaps the greatest philosophical shift would be accepting that some mysteries aren't puzzles to solve, but limitations to navigate. The night sky has always been a mirror reflecting back our assumptions. First, we saw gods in the stars, then laws of physics. Now, we're glimpsing cracks in the mirror itself, hints that the universe isn't just stranger than we imagine, but stranger than we can imagine. Spectral shadows don't just hide objects, they hide entire ways of being, waiting for us to develop the tools and the humility to see them. Every mystery attracts its share of false alarms, and spectral shadows are no exception. The internet brims with blurry videos and sensational headlines claiming invisible giants blocking stars but dig deeper, and most crumble under scrutiny. Take the infamous Black Knight satellite conspiracy, where enthusiasts pointed to supposed ancient star dimming as evidence of alien megastructures. The reality, those fluctuations traced back to camera malfunctions in early space missions, their erratic data misinterpreted as celestial phenomena. Then there's the UFO factor. When a star dims unpredictably, it's tempting to link it to extraterrestrial activity, especially when the dimming pattern seems artificial. But science thrives on ruling out the mundane before leaping to the extraordinary. In 2019, a viral study claimed repeating dimming intervals around a distant star signaled an alien construction project. Further analysis revealed a simpler culprit: internal telescope noise, compounded by software glitches that artificially amplified minor brightness dips into false signals. The lesson: extraordinary claims demand extraordinary evidence and rigorous error checking. Camera artifacts pose another persistent hurdle. Satellite streaks, cosmic ray hits, and even moisture on telescope lenses can mimic shadow-like dimming. Automated sky surveys sometimes flag these glitches as potential discoveries, requiring human verification to separate cosmic ghosts from technical gremlins. One notorious case from the Gaia satellite data involved a star that appeared to vanish until astronomers realized a fleck of space dust had drifted onto the lens, creating a temporary blind spot. Even natural cosmic phenomena get mislabeled. Fast radio bursts, intense millisecond flashes of radio waves, were once theorized as shadow-related until traced to magnetars, highly magnetic neutron stars. Similarly, dark galaxies devoid of stars were proposed as shadow sources until radio telescopes mapped their faint hydrogen clouds, proving they were ordinary galaxies cloaked in dust. The danger isn't just false positives. Overzealous debunking can also obscure real anomalies. When Tabby's star first made headlines, skeptics dismissed it as interstellar dust, only for subsequent studies to show the dust itself behaved unlike anything in known models. The line between myth and breakthrough often hinges on patience, with truth emerging slowly through repeated observation. What separates legitimate shadow research from the noise? Peer review, reproducibility, and a willingness to say we don't know. While hoaxes chase viral moments, science embraces uncertainty, collecting data, testing hypotheses, and discarding what doesn't fit. The shadows that survive this gauntlet, those are the ones worth chasing. The enigma of spectral shadows lingers like a whisper at the edge of our understanding, a cosmic riddle written in disappearing ink. Whether they're fingerprints of dark matter, echoes of higher dimensions, or relics of civilizations lost to time, these fleeting absences in the starlight force us to confront a humbling truth. The universe is far stranger than our textbooks dare to admit. For every celestial phenomenon we've catalogued, there may be a dozen more hiding just beyond the reach of our telescopes, sculpted from physics we haven't yet imagined. What makes these shadows so thrilling isn't just their mystery, it's what they reveal about how we explore the cosmos. Each unexplained dimming is a crack in the facade of our knowledge, an invitation to question assumptions we've long taken for granted. When a star winks out without a trace, it's not just light that vanishes, it's the illusion that we've mapped the frontiers of reality. The greatest discoveries often begin with anomalies, with data points that refuse to fit. And right now, scattered across the galaxy, countless stars are flickering in ways that defy every model, every equation, every carefully constructed theory. This isn't a failure of science, it's science at its best, a living, breathing process that thrives on the unknown. Centuries ago, sailors mapped coastlines with the warning, "Here be dragons," at the edges of their charts. Today, our celestial maps carry similar blank spaces, not from lack of trying, but because the universe insists on keeping secrets. Spectral shadows are our modern dragons, lurking in the uncharted waters between the stars. Yet the tools to chase these phantoms are sharper than ever. From AI sifting through starlight to lunar telescopes peering into the cosmic dark, we're building instruments that may soon turn whispers into answers. And when those answers come, they won't just solve a puzzle, they'll rewrite the rules. Every shadow we decode could unveil new forms of matter, new forces of nature, or even new chapters in the story of life's place in the cosmos. So keep watching the skies, share the mystery, debate the possibilities, because the most exciting thing about spectral shadows isn't what we know, it's what we've yet to discover. The cosmos is full of shadows, and every flicker of starlight holds a question. What will we find when we shine